Okay, I think we'll get started. Welcome, everyone. So, can you remember the last puzzle that you solved? Maybe it was a Rubik's Cube or a jigsaw puzzle. How about this one? Can anyone figure it out? Well, it's the title of my talk. And I wanted to start with this because solving puzzles is a similar mindset to reverse engineering. Especially puzzles that you start with the solution or the answer to the puzzle and work backwards to figure out how the pieces fit together. So you would have come in here expecting reverse engineering a classic video game, and you probably would have seen the reverse and immediately got it. So we've got reverse, and this is obviously an engineering. A classic video game. And did anyone get the last two? So this next one is a game called The Incredible Machine, or TIM. So my name is Tim Comport. So for as long as I can remember, I've been fascinated by technology, and I've really learnt best by pulling things apart and sometimes putting them back together again. So this is me pulling apart an 80s big track programmable robot. Does anyone have one of those? Oh, I got one. So yeah, I pulled it apart and made it into a better robot. But I also like pulling apart software to see how it works. And there was one of my favorite games, actually BioForge, which we're going to talk about today, that about 20 years ago when I was 17, I started tinkering and pulling it apart. And over the years, I kept coming back to it. And recently I was looking for a project to play with .NET Core. So I figured I'd start porting all the code that I had written to .NET Core just to make it cross-platform. So I'm going to share with you some of the things I've learnt doing that. But where do we start with reverse engineering? So there's no silver bullet, and there's many different disciplines for reverse engineering. Really, the only common denominator is a lot of time. But I've already said reverse engineering is like solving a puzzle. So maybe we can use that as inspiration. So I'm sure you all know how to solve a jigsaw puzzle. So you start by looking at the image of the puzzle on the box. Sort the colors or the features into different groups. And then you would probably start with the edge pieces, start at the border and build it up, completing the different groups. So how can we make these steps a bit more generic to help us? Well, studying the image is like researching the target. So that's what we're going to start with. We're going to learn a little bit about BioForge. And another way of saying identifying the colors or features and sorting them into groups is to identify the overall structure. And instead of start with the border, a little bit more generic, start at the boundaries. And really completing the different color groups is another way of saying divide and conquer. So this is the steps that we're going to use. So our target is BioForge. So we'll start with step 1. We need to learn a little bit more about BioForge. So to do that, we're going to go back almost 25 years through video game history, back to March 29 in 1995. So this is the award-winning box art for BioForge, and I've got a copy here, still sealed, from 1995, which I paid way too much for on eBay. BioForge was really the first game I can remember where the images on the box were actually not just artist impressions. They really lived up to what they showed. There's a few A couple of things that I want to note before we continue though. So firstly, it is copyright. I'm not a lawyer, but I did chat to an IP lawyer in preparation for this talk. And I just want to say that in giving this talk, I'm not suggesting or encouraging you to infringe any copyright laws. So if you are reverse engineering anything, just be mindful of the legalities. And if you're unsure, have a chat with a lawyer. In this case, BioForge copyright is owned by Electronic Arts, and you can still buy BioForge on Good Old Games. It's about $8. Just another thing to note, BioForge is mature rating, and at the end of this talk, there will be some pixelated blood. So if
that's what I'm out of here.
So to learn a little bit more about BioForge, I've just got some clips here from the game. So it's really a DOS adventure game where you play a character that has amnesia. You've been abducted and turned into a cyborg assassin. And really the game is about exploring the planet that you're stuck on and solving puzzles using items. One of those puzzles I remember fondly is you have to use a severed arm to get through a hand scanner to open a door. And although it was critically acclaimed, it didn't really sell that well. This could have been because it was really hardware demanding. So at the time it required 8 megabytes of RAM and 486 with 33 megahertz. This was before the time really of hardware graphics acceleration being commonplace, and so BioForge used a software 3D renderer, which meant that it needed that really high-end hardware. One thing a lot of people don't know, even if you have played BioForge, is that it was the first game ever to use 3D texture mapped characters. So this is pretty commonplace in every game these days, and it started with BioForge. So the developers were very pioneering. So this is another cyborg that you had to battle. It really has diverse, environments, but to cope with the hardware, they couldn't make all this 3D. So you're dealing with fixed camera angles and pre-rendered environments. So if anyone played the game, has anyone played the game? No. So this scene here is one of the most frustrating puzzles. You have to get the timing exactly right. So now that we know a little bit about the game, we're going to move on to step 2. So identifying the overall structure of the game. And to do that, all we're going to do is just have a little bit of look through the files in the game. And this is really my first tip if you want to prevent your software from being reverse engineered, is don't deploy the artifacts with such good names in really well-named folders, because that's like already having the colors of the puzzle pre-sorted. So you can see here we've got some directories. This one contains presumably files to do with the character, 3D character models. In here we've got some files that end in the extension FNT. So they're probably fonts. We got, if you played the game, you would realize that these are the names of the different levels. So we've got some level files. All the different items, 3D items that you can pick up in the game. There's different dialogues in the game. So these all have the extension .cam. And under music, we've got a music.flx. Then we got rooms that also have the extension .cam. Then interestingly, we've got 126 odd scripts that are actually quite readable. So all the game logic is in there. And then we have an intro endgame SHO file. And finally, we've got sounds. So presumably this is English samples.flx. So another way we can look at the files in the game is if you fire up like Windows Subsystem for Linux or a Linux box, the file command in Linux is really helpful. So I'm going to run this, the file command on all of those files and see what we get. So most of this is either false positives or not very helpful, but it does pick up one file. So it's saying these .sho files are FLC animations. So this is an Autodesk Animator format back in the day, and it's given us quite a lot of information. So this is really helpful. We can see if we can open these up in VLC. So there we go. We can already play some of the movies from the game. Well, it's a little bit glitchy. VLC reader for this format isn't the best, but that's all right. The FLC format has a documented specification, so we can write a reader from that specification. Okay, so after looking through the files, this is kind of what we've worked out. We've got all these different formats, and you might be tempted to say, well, we're reverse engineering a piece of software. Why don't we just disassemble the executable, which I've done, and I ended up with 250,000 lines of assembly. But then I thought about it a bit more, and from the research we've done, we know that BioForge uses a software 3D renderer, which would be a substantial amount of that code. But we don't need the software 3D renderer anymore. We have hardware accelerated graphics libraries. And all of the game logic is contained in those scripts, the SCP files. So really, disassembling the executable is not going to give us that much. Obviously, we've got limited time today. We've got half an hour or so to try and reverse engineer and recreate this game. So we're going to go with step 3 and start at the boundaries. So we've already seen that we've got the SHO movies, albeit without any music or sound. They're silent. And we're going to focus on recreating the intro and title sequence to the game. To do that, we need at least these 6 formats. So we already have the movies. So let's move on to the fonts. So we're going to spend most of our time here because the tools and techniques that I use on the fonts is really exactly the same as the other formats. So where do we start? Well, you might have noticed that those 4 steps were really recursive. So when you divide and conquer, you can go back to step 1 and research and so on and so forth. So let's research a little bit about fonts. So I haven't included all of the exhaustive research that you might do here, but the things that are key. So in BioForge, the fonts are used for subtitles and menus and credits. And it's likely, given the age of the game, that the fonts will be bitmap fonts rather than vector-based fonts. So a bitmap font, you'll need a matrix of pixels with a given height and width. And also original IBM PCs used extended ASCII, so code page 437, which is 8 bits for 256 characters. BioForge was multilingual, so English, French, and German, so they needed to use some of that extended ASCII. But also, as with any ASCII, the first 32 characters are often non-printable, so that'll be key. So against better advice, I'm going to do a live demo with a hex editor. Sorry if this makes you squirmish, but I'll hopefully be able to break it down for you. So we've researched the fonts, so that was step 1. Step 2 is identify the overall structure. So a good way to do that is if you look over here at the minimap. So I'll just bring up a pen so I can highlight some stuff. So if you look over here, you can see there's clear sections here in the file where the data structure changes. So if we jump down to that first section and have a look at where it starts. So we can see it's around 410, maybe 4109 or 410A in hex. So if we move on to step 3 now, which is start at the boundaries, we'll jump back to the top of the file. And if we have a look from the start, we've got some numbers here that we don't know what they mean yet. But then we find something that looks interesting. So we've got here a 4-1A in Little Endian. So the byte order is reversed. So that's actually what we just saw as the start of that next section. So this must be an offset to that first section in the file. So if we keep scanning along, so we've got a 4-byte offset there, and then it looks like we've got 3D and then 457. If your hex calculations are any good, you would have noticed that 41A plus 3D is 457. So this must be like a size. And then we've got another offset. So we've got an offset, a size, and an offset. And this actually continues. So we've got offsets and sizes. And if you keep continuing that down, you find that there's actually 174 offsets and sizes. And that number there, AE, is 174. So it looks like we've got a bit of a header here where it's telling us the number of offsets and sizes which immediately follow. So if we jump back down to 41A, and we select that 3D number of bytes. And we're going to copy that as a hex string and paste it into a new file. Just make sure it's uppercase and turn word wrap on. So it makes sense if this is meant to be a font that this is a character in that font, the first character. So we can actually restart those 4 steps again. We don't need to do any more research, but if we look at the overall structure of this data, we can see that there seems to be sort of 3 sections here. So we've got all these 1s at the end. So let's split those off. And then you might notice that there's these numbers decrementing by 1. So let's split those off. So there seems to be 3 sections here. So some sort of header to the character. And then if you look at these, they seem like some kind of offset, maybe a relative offset because the numbers are so small. But this doesn't look like a character at all. It looks like nonsense data. So that's a little bit of a bust. But remember from our research on fonts that it's most likely that the font file is using the fonts stored in like an ASCII order in the file. And we know that the first 32 characters in the ASCII table are often non-printable. So that kind of meshes with what we just found, that first character was nonsense. So if they are stored in ASCII order, if we pick a character that might make it easier for us to see a pattern, that might help. So I've picked capital H because it has some vertical and horizontal structure that will make it easier to spot. So this is decimal 72. So let's jump back. And open up our calculator. So if we have our offset table has 4-byte offsets followed by 2-byte sizes. So each item in that table is 6 bytes. So we say 72 times 6. But we also had 6 bytes preceding that table, so we'll just add another 6. So this gives us 1B6 for what should be the offset for the capital H. So let's go to 1B6. Okay, so if our theory is correct, this should be the offset within the file to a capital H, and this should be the size of the data for the H. So let's go to, remember it's little endian, so 20 F7. And we'll select the size and we'll copy that to a hex string, put it in a new file, just make sure it's all uppercase, turn on word wrap. All right, so we didn't go totally bust on that first character. We learned that the characters seem to have 3 sections to them. So let's split this up into those 3 sections. So we've got 75, 74. So this is the 3 section for what should be a capital H. And we were saying before that these look like relative offsets. So relative just means not absolute within the file. So this 28 actually points to the start of this section. And then the 27 is 1 byte in from that. And then we've got 26, so another byte in from that, and so on and so forth. So if we split this data up based on those relative offsets, we end up with something like this. I've actually not selected all of the data. So let's just do that again. That can go away. I'm just gonna all right, so let's get back to where we were. So we split the data up based on those relative offsets. Does anyone start to see any kind of pattern? It'll be a revelation. So I'm expecting a cheer once this is done. Okay, so anyone see what we're expecting? Maybe it helps if I... So we were expecting a capital H, and it looks like that's what we have. It looks a little bit skew if there are some other numbers in here that have some meaning. So we can see that these offsets are really the number of rows. So we can actually see up here in this header that it's telling us that it's giving us a width. You can see every row has numbers that add up to 8, and it's also giving us a height, so the number of rows. So as I said, the numbers in each row add up to 8. So we must have 8 pixels width. And if you look at these numbers, you can see that every FD is preceded by a number that is the number of FDs following. So that's really just telling us the number of pixels that is following. And then there's other numbers preceding that. And if you think about it, they're really just number of pixels to skip, because this is 4. So if we space that out, so it's 4 pixels, then our H is really lined up, so on and so forth. So it looks like we've figured out how to read the font files. So this is a simplistic overview of what we just found. So we found we had a font header, we had the offset tables for the character records, followed by all the characters in ASCII order. And each character we found had those 3 sections: the character info, followed by row offsets, and then each row of the character. We found that mini algorithm with the skip count, followed by the number of pixels and the pixels themselves. One thing to mention is that you might have noted there's a bit of redundancy here. So if it's telling us the number of pixels that follow, then there's really no need for it to have all of those pixels. It could have just said, 8 FDs. So this is what's called run length encoding. So they could have compressed the font files if they used run length encoding. That'll come in handy with one of the other formats. So that's the simple overview of what we found with the fonts. So let's have a quick look at some code. So I've got a font reader here. It's really just using a .NET binary reader. And it's very simple. We're just going through, reading in the different bytes that we found, whether it's a short, so 2 bytes, or an integer, which is 4 bytes. So it turns out that those first 2 shorts at the top of the font file were the maximum height and the maximum width of all of the characters in the file. So we're reading those in here. And then we remember we had that third short, which turned out to be the number of characters, so the number of offsets in that table. So we're reading that in here. And because we're going to be using OpenGL to render everything, we're going to basically represent the font as a texture atlas. So it's basically just an image with all of the font characters and their pixels. So then we use that offset table to jump to the first character, and we loop through each character. And there was some data in there that doesn't seem to be useful to us, but we did see that that header for each character had the width and the height of the character, so we'll use that. And then we'll use those relative offsets to jump to the rows for the character. And then we'll loop through those rows, and this is that little algorithm that we discovered. So there was a number of pixels to skip. We'll read that in here and skip over those pixels. Then we read how many pixels are following, followed by the pixel itself. So we read that into the texture atlas. So I've got a little demo here that will run. So this demo is really just dumping out the texture atlas to an image, just so we can see. So you can see there we've read in one of the fonts, but there were a number of fonts. So let's just try one of the other fonts to make sure that it's the same. So that was 0.font. We'll try another one. So there you go. If you're paying attention in the video, the clips of the game, this was actually the font used for the subtitles. Okay. So now we've figured out the font file format, and everything else gets easier from here on out, because all of those techniques are all that you need to know for the other formats. So we'll move on to those 2 FLX files that we saw. So they were helpfully named music and esamples.flx. So back to our 4 steps. The first thing we do is research our target. So BioForge has both music and sound effects. And helpfully, the install guide for BioForge actually tells us that the music is general MIDI. And the standard for digital audio is really pulse code modulation. So that's a fancy way of saying, sampling the waveform at a uniform rate and quantizing those samples into commonly an 8-bit or 16-bit number. And it's usually either signed or unsigned, and there's a range of common frequencies for PCM. So I am just compressing all the research that I did into the key bits of information that we need to be able to reverse engineer the sounds and the music. So I'm not going to do the hex for this one because it's really actually even easier than the fonts. So did exactly the same approach, looked at the minimap in the hex editor to look at the overall structure, determine where the offsets are. And this one turns out to just be like a container file, so a lot like a zip file, but uncompressed. And the items within the container are really just MIDI files or raw PCM audio. So let's have a look first of all at the music. Actually, so I've got a common reader here for the FLX file, so a flex reader. You'll see a lot of similarities with the font reader. So I've got a bit of a header here. It's a bit larger than the fonts. It's got some comments and things like that. And then it just has an offset table similar to the font to be able to locate each of the items, essentially files within the container. And to read out each item, it's just jump into that offset and spitting out that byte array. And then all we need is the MIDI files are actually extended MIDI. So just got a converter to be able to convert from extended MIDI to MIDI because MIDI is more commonly supported. So let's have a look at the music demo. So for this one, really just using that flex reader to open the file and loop through all of the items within the flex file and spit them out as MIDI files to disk. So let's run that. And have a listen. So if you've played BioForge, you would recognize this tune, although it sounds a little bit different to the game because we're actually just using the general MIDI sound font that's included by default with Windows. So it does sound a little bit different. So let's go on to the sound, which are a little bit more interesting. So recall from the research that with the sounds, it was raw PCM, and there was, it could be 8-bit, 16-bit, signed, unsigned, and a range of common frequencies. So I could have analyzed the data and tried to work that out, but because the number of combinations is so small, I literally just brute forced it and went through all the different combinations until I could see that I had the right one. So I'll show you what it sounds like first, and then I'll go through what it might sound like as I was working through those combinations. So again, I'm just dumping out the sound to, in this case, a WAV file. So there's 718 sound effects. So there's a interesting one here.
A logbook.
This is Marine Dropship Roanoke to control.
So that's how it is supposed to sound. But if we have a look at this raw to wave converter. So this is really just writing out a wave file. The actual data is dumped straight out. All of this is just the wave header. So as I was going through the different combinations, so we'll say change the frequency and see what happens.
This is Marine dropship Ronick to control.
So you can see that it's not right. And similarly, if originally I didn't realize what sign the bytes were, so I got something a bit like this.
This is Marine dropship Ronick to control.
So you can still hear the audio there, but it's not quite right. So that was really the only difference with this format, was just using that brute force approach to go through those different combinations to get the sound effects correct. Okay, so we've now got the movies, we've got the fonts, we've got the sounds, we've got the music. So next is the cameras. Now, the word cameras may not make sense to you just yet. So I'll show you a few examples. So I mentioned it during the clips that I was playing, but due to the hardware limitations, they couldn't do a 3D world. So instead they created the 3D world and then pre-rendered different fixed camera angles to just 2D images, although they did make the images animated. So a couple of examples here with the equivalent pre-production image. So our research for the cameras is that they're really a bit like a layered GIF file. So they can have a number of different animations in different layers. So we know from looking at the game that it's most likely VGA, mode 13 hex, which is 320 by 200 at 256 colors. And again, just an image is a matrix of pixels. We're going to have a red, green, blue in the pixel, 1 byte for each of those. Likely to be some kind of color palette. And I mentioned when I was doing the fonts about run length encoding. So that's really the most basic form of compression for images. So if there is any kind of compression, it's likely to be run length encoding. So again, I'm not going to go through the hex because it's very similar to the fonts. And it actually turns out, although the cameras have the extension .cam, they turn out to just be the FLX or flex container format, which we found with the music and the sounds. So within the flex container, it has the different layers for the images. And I've figured out that the first item in the container was actually a color palette, because I noticed across all of the files, the first item was always 768 bytes. And recall I said that it's 256 colors. So RGB, 256 colors is 768 bytes. So I figured that must be a color palette. And then each layer of the image, again, just splitting it out, dividing and conquering. Very similar layout again with a header, offsets, and each offset has a different frame within the layer. So really just like a GIF. One thing that helped here was recall that I wrote a viewer or a reader for the SHO files, the movie files. So because that was a format from the time, they really used similar concepts and ideas for storing images, animated images at that. So writing that reader for the SHO format really helped to understand this format as well. So let's have a look at a demo for the camera files. So this one's a little bit more interesting. So we've got our camera reader here. So we're reading in that structure similarly to the fonts again. We've got width, height, frame count in the header for each layer. But let me just jump down to the bit where we actually read in the pixels of the images. You can see here that they actually switch between using compressed and uncompressed per row of the image. So if you think about run length encoding, it actually makes the size larger if the pixels are always changing frequently, because you're essentially having 2 bytes the number of pixels following. So depending on how uniform the pixels are in your row, it makes sense to use run length encoding or not. So they actually change that from row to row in the image. So if it is compressed, run length encoding, then we read the number of pixels that are going to follow, and then just repeat that number of times. And if it's not run length encoding, then within the loop, we just read every pixel. So within the demo here, I've got, we're first just going to dump out all of the layers and frames within one of the cam files. I've selected an interesting one here, Beach B, which you'll recognize. So let's run that. So you can see we've really just got all these pieces of an image, different layers of the image and frames of an animation. So looking at those images, we can actually form a composite image and actually output it as a GIF. So there we go, we've recreated that part that we saw from the actual in-game clip. All right, almost there. So we've got the movies, we've got the fonts, we've got the sounds and the music, we've got the cameras. So now we just need to glue it all together, and we need some of the scripts to do that at least. So let's have a look at the scripts. So my next tip for making your own software harder to reverse engineer is don't put your comments into your production artifacts. So all these scripts actually have comments spread throughout them, and the scripts themselves are partially compiled. They are human readable somewhat, but the comments are definitely human readable. And I actually had to censor this one. Another interesting comment here is this one. I kept on mentioning the hardware limitations at the time, and they had to change the speed of the movie so that the sound effects and the music could keep up on double speed CD-ROM drives. So that's the era that we're dealing with. All right, so if we have a look at this, because we're trying to recreate the intro and title sequence to BioForge, so I've opened up the script helpfully named intro. And looking through this, we can see a lot of things that line up with the intro if you've watched it. And recall that I said that the movies didn't have any sound or music associated with them. So they actually needed scripts to synchronize the sounds and the music with the silent animations. So you can see here that really they've got timings of the animations, and this can only be some kind of synchronization with the sound effects and music. Now I'm using Notepad++ here because I couldn't work out how to do this in Visual Studio Code, but it's more helpful if you look at the hex codes for the non-readable characters. So we can quickly determine by looking at the different scripts that these are commands for play a sound effect or play music. And then these ones, there's some other files in with the scripts with the extension .def, which are really just a big enumeration of all of the sound effects and the music. And with a little bit of brute force, I was able to figure out that these are really just indexes into those enumerations. It's using like a XS128 representation for the numbers. So given all of that, I was able to put together a bit of code that played the sound effects and the music at the right times in the animation. So we've got BioForged. So BioForged, I've, as I said, used .NET Core with OpenGL for the graphics, and Fmod sound library to keep everything nice and cross-platform. We've already seen all of the readers, really. So all that's left is to play it. Suggest that I should start this minimized so it doesn't look like I'm cheating. Oh, actually, we should change our signed. Yeah, so we'll switch that back. So another way you can tell I'm not cheating is, again, all of the sound effects are using the Windows default sound font. So the music does sound a little bit different to the actual game.
This is Marine Dropship Ronik to Control, making final approach for delivery of supply requisition B9/3Q.
So this is the SHO intro animation synchronized with the sound effects, which are the voices you can hear, and the music in the background, all put together using the scripts. And soon we'll get up to the scene that actually has to slow down because of double speed CD-ROM drives. I had to also slow it down to make sure all the script synchronization is correct. And remember my warning, there is some pixelated blood. So yeah, if that makes you uncomfortable, you might want to leave. So this is really the character that you play has been abducted, and he's about to be taken into the base where they'll turn him into a cyborg. As I said, if you're interested in playing the game, it is available on Good Old Games, and it's playable using DOSBox. It is in the top 100 games, DOS games that you should play, according to the internet. So look away now if you're squeamish. So this is the scene that I actually had to slow it down. So I always thought that they slowed it down to make it feel dreamlike until I read that comment in the scripts. So that's the intro sequence, but we also, once this finishes, we also were able to recreate the title screen. So the hand here is a .cam file. It's one of those, and the background is a .cam file. And the buttons are .cam files with animations for the mouse over, and we have, the beautiful font that we reverse engineered. So we've only really touched the tip of the iceberg here. So if you're interested in learning more, you can follow me on Twitter. I'll be tweeting once I've uploaded all the code onto GitHub, including the rest of the game. We'll be doing it in time for the 25th anniversary of BioForge, which is March next year. Or if you want to have a chat about any of your reverse engineering projects, I'll be outside afterwards. Thank you.